Hello all, welcome back to the part C of lecture 9. In this part we are going to talk about the bootstrap regression, and bootstrap statistics is an algorithmic strategy which typically resort to a simple random sample with replacement strategy, or sometimes without replacement, but mostly it resort to with replacement strategy. Now, it falls under the broader class of resampling strategy. That means if you have a sample, say if you have a sample y which have some values y1, y2, dot dot dot, yn, what we will do, we will draw, this is main data, okay, this you can consider as your main data, and this is your main data, and what we will do, we will draw random samples from this data. Okay, so we will draw random samples from this data. Now this data itself is a sample from the population. Now we are drawing random sample from this sample, so that's why this new sample, maybe y1 star, y2 star, yn star, this sample will be called resample. So resample, and this is a broad class of algorithms are there, and this strategies are called resampling strategy or resampling algorithms. This idea of bootstrap was first introduced by Professor Brad Efron in 1979 in his Annals of Statistics paper. The idea, though apparently simple, it's a very simple idea, but it revolutionized the statistics by its ability to replace analytical derivation by brute force computing. So this was, I think, was very timely with respect to an advancement of personal computer, etc. And this pretty much revolutionized the idea. First, I will present the idea of bootstrap statistics with respect to one univariate sample or univariate variable, and then I will describe, once you get the idea of bootstrap statistics, what I will do, I will present the idea of bootstrap statistics in predictive model or regression context. So suppose y1, y2, yn are IID observation from any probability distribution. So we are calling it, say, F. F could be normal, F could be Gaussian, anything. So F could be any probability distribution, okay. So and Tn will be some function of the data. Tn will be some function of the data y1, y2, yn. This is a statistics which estimate the parameter theta. Okay, so theta is some parameter of f, is some parameter of f, f is the probability distribution, completely unknown. And what you are using Tn, the sampling, which is a function of the sample. It tries to estimate, Tn tries to estimate the theta. Now, as usual, the sampling distribution of Tn will depend on f. Sampling distribution will depend on the population distribution. F is the population distribution. So the bootstrap idea is in simplest form is to estimate. So F is unknown, the population distribution is unknown. So what we will do, we will estimate the unknown population distribution by the empirical probability distribution. What is empirical probability distribution? Very simple. Empirical probability distribution only is defined as something like this: 1 by n summation I equal to 1 to n indicator function xi less than equal to small x. Okay, so what is indicator function? Indicator function is, if condition A is satisfied, then I will call 1 or 0 if A is true, 0 otherwise. So that's how it is being defined. It's a simple function. You can define it. It's very easy. Just like, you can write a for loop and define the function in any program. It's just like 3 lines of code. So the empirical CDF is, and here is the big result. The big result tells you, big theoretical result that tells you that empirical CDF of Fn, CDF that this function is a non-parametric maximum likelihood estimate of the CDF, unknown CDF. So if you have an unknown probability distribution, the best guess that about that unknown distribution you can make is through this particular distribution, empirical CDF Fnx 1 by n summation xi indicator function summation xi less than equal to small x. This empirical CDF, you can code it in like single, pretty much in 3 to 4 lines. That's it, 3-4 lines of our Python code or R code. So the bootstrap based on this empirical CDF is called non-parametric bootstrap. Now bootstrap statistics is, suppose y1, y2, yn are IID observations with CDF F, and Tn y1, y2, yn is a statistics which estimates the parameter theta. Okay, so since the empirical CDF is the non-parametric MLE of CDF, now what we can do, we can draw sample from Fnx. This empirical CDF, we know how to draw sample from empirical CDF. This is simply, now turns out that drawing from empirical CDF is same as drawing sample, IID samples from your data y1, y2, yn. That's it. So that is why the resampling comes in. So you draw sample from, if you draw resample, that is, if you resample from y1, y2, yn, suppose that comes y1 star, y2 star, dot, sorry about that, let me just a little bit write it carefully, y2 star, dot, yn star. Suppose this is the resample data from y1, y2, yn. Now these resamples are basically same as drawing sample from empirical CDF, which is maximum likelihood estimate for unknown probability distributions. And hence we can draw as many times, we can repeat this resampling as many times as we want. So that is the main idea of bootstrap statistics. So let me explain you the bootstrap framework now. What is the framework? So you have these you're starting with this data set, that this is the data set that you have, and you are assuming these are IID random samples from an unknown distribution f of x or f of y. Some unknown distribution f, completely unknown, you have no idea. It could be normal, gamma, log normal, you have no idea. Now you can also do, you can estimate the Tn with some method. Using some function, you can estimate the Tn, which is a statistic for estimating parameter theta. Estimation is not an issue. What is in problem is you don't know what is f, so you don't know what is the sampling distribution of Tn. So you don't know what is the variance of Tn is unknown. Variance of Tn is unknown. Confidence interval of Tn is unknown to you. So you cannot compute the margin of error. You cannot do any statistical inference. So what is the approach? Then you resample YNB star from Yn. From here, from this data set, you just resample. These are your resamples, and you resample many times, as many times as possible. So this capital B is, you decide. It could be 1000 times, it could be 10,000 times, it could be 100,000 times, it could be 1 million times. You decide how many times you, depending on your computational ability, you decide. Once you compute, once you resample this YNB, or for this YNB you can calculate again the statistics TNB. So for each resample B, we can compute this TNB star, and once I get all these TNB stars, so I have this resample estimate of TN1, TN2 star, TN3 star, all these estimates, TNB star. Now based on these data, I can have a sampling estimates of the sampling distributions. Some I can draw the histogram. Okay, I can draw the histogram, and I can get a sense of what is how the histogram looks like. Okay, and based on this histogram, I can calculate what is these values, we can calculate what is the variance of Tn star, TNB star, and what is the confidence interval of TNB stars. So remember that what we don't know is variance of Tn and confidence interval of Tn. But using TNB star, I can calculate variance of TNB star and confidence interval of TNB star. Now, so let me repeat the Bootstrap framework again. So from the main data, we resample the data, and for each resample we compute the statistics, and based on statistics, so there's basically Tn1 star, Tn2 star. For each resamples we compute Tn capital B star. Capital B, you decide, user decide, it could be 1000, 10,000, whatever. Now based on these computation, you can take the average of these guys, you can calculate the variance of these guys, you can calculate the confidence interval of these guys. Now you can also define empirical distribution GB, this guy's scaled GB. So all these things you can do. Now due to strong law of large number, as capital B goes to infinity, remember the capital B is user defined, so you can make it as much large as possible. Okay, one can show TNB bar converges to Tn almost surely. The variance of TNB converges to variance of Tn almost surely. Confidence interval converges to confidence interval of, like, resampled TNB is converges to confidence interval almost surely. And sampling distribution or bootstrap sampling distribution converges to f of Tn. Now what is happening? What we don't know, because f is unknown, because the population distribution is unknown, f is unknown, true population distribution is unknown. So because of that, ftn is unknown. Because ft is unknown, variance of Tn is unknown. Because if variance of Tn is unknown, you cannot compute the confidence interval of Tn. So that is the main problem that we are facing here. But what Bootstrap Statistics is saying, that you don't have to worry, all you have to ensure you have enough computational capacity, push the b to infinity, and variance of Tn will converge to variance of Bootstrap Tn will converge to the variance of Tn. So that means basically variance of Bootstrap Tn will be same as variance of Tn. Similarly, confidence interval of Bootstrap confidence interval will be same as Bootstrap actual confidence interval of the Tn. So this is the strength of the work. Now this is the idea of the Bootstrap statistics. Now I am going to explain you Bootstrap statistics in context of regression. So now we are going to talk about Bootstrap regression. So let us consider the model yn xn x beta plus epsilon. Expectation of epsilon is 0, variance of epsilon is sigma square in. So homoscedasticity is still I am holding. But what I'm now giving up is normality. So most of the time what we are seeing, that at least in the capital asset pricing model, what we have found that homoscedasticity was okay, even the randomness was okay, but what was not holding good was residual was definitely not normal. Since the residual was not normal, so now what we are saying that okay, residuals are coming from IID distribution, but we don't know what is the distribution. So we are saying f is unknown CDF. Since f is unknown CDF, we cannot do any inference on beta. So we can estimate the OLS estimator. OLS estimator is all you do is x transpose x inverse x transpose y. That not a big deal. You can even calculate variance of beta n hat, sigma square x transpose x inverse y, but you cannot do the confidence interval. You cannot calculate the confidence interval. So that is where we are getting stuck. So what to do? So what we can do is we can look into the residual. What is residual? Residuals are epsilon equal to y minus x beta n hat. We can error equal to this, and error equal to ei equal to yi minus xi transpose. It should be not epsilon, it should be ei, because it's observed. We are using x beta n hat here. Now what we can, so we can have these observed error. Now suppose fn is the empirical CDF of this error, okay, small e. So now what we are saying that, all right, these E star, EB star follow IID fn. Then EB star is resampled from E using SRS with SRS WR, where B equal to 1 to B capital B could be anything, any big number, 10,000 or 100,000 maybe, yeah, whatever. Now you calculate, all you have to do, just you know what is x beta n hat, just add epsilon EB star, then you get a new response YB star. And once you get the YB star, All you have to do, you get estimate the resample coefficient. You can estimate as X transpose X inverse X transpose YB star with a new response, new bootstrap response. But turns out you can write it as beta n hat, which you already know, plus X transpose X inverse X transpose is EB star. Okay, now X transpose X inverse X transpose you already know, right? So EB star, all you have to do is multiply, and that will give you the beta n star hat. And one can show that expected value of beta n hat star bootstrap is beta n hat. One can show that. It's not a very difficult thing to show. So wow, what is my bootstrap estimate? Bootstrap estimate is simply you take the average of all these resampled estimates and calculate the variance of all these resampled estimates. Okay, so this is my bootstrap estimates. Now this is, and based on these bootstrap estimate and bootstrap variance, you can do the simple statistical inference. Now there is no problem because you are not even making any assumptions. Now there is another approach. This method was called residual bootstrap regression. Okay, this method was called residual bootstrap regression because you are doing resampling the residuals. You are resampling the residuals. Okay. Now suppose, but you are assuming that your homoscedasticity holds good. Homoscedasticity is okay. Your data still preserve the homoscedasticity, but we have seen previously cases where homoscedasticity even not working. Now there were cases where we have seen, there were case studies where we have seen that homoscedasticity was not working. In that case, you cannot use residual bootstrap regression because residual bootstrap regression still assume that your data has homoscedasticity. But if the homoscedasticity doesn't work, then you better go for paired bootstrap model. In the paired bootstrap model, what you do is very simple. So you are assuming y, same model, y equal to x beta plus epsilon, but now you are assuming variance of epsilon could be any sigma. It could be any sigma, and yi, xi star are following if some unknown CDF. Now from the DB, from the data size, you just resample the yi star, xi star as a pair. As a pair you resample, and you resample many times, and do it for each resample. You have to calculate these OLS estimates. Remember that in this case what will happen is the OLS estimates are not necessarily you have to calculate this inverse all the time. In the residual, in each resample you have to calculate this inverse, but in residual bootstrap you don't have to calculate this inverse because you do it once and you are done. All you have to do, you have to just draw the residual sample and add this to the residual sample. That's it. Okay, so in this case, but you have to do this, and then the simple bootstrap estimate and confidence estimates and variance and confidence interval can be done in the regular way. So if If the residuals are heteroscedastic, then paired bootstrap is still consistent estimator, and you better use paired bootstrap and try to avoid the residual bootstrap. However, in case of heteroscedastic residual, the residual bootstrap is not a consistent estimator. So be careful about this. So here is some example that what we found that in the OLS estimate with the simple Z t-value based regression analysis, which assumes the residuals follow normal distribution, in paired bootstrap case, what we found is that the bootstrap estimates is actually converging to the OLS estimates. So in that way, estimates is not a problem and almost close to the both alpha and beta, very close to the OLS estimates. Standard error can also be somewhat similar, but little less in this case. However, and we can compute the confidence interval. Perhaps this is the correct confidence interval given for the OLS estimates, given that we are assuming that the original distribution could be anything, the residual distribution could be anything, whereas this was assuming normal, and we found that the normality is not a valid assumptions. And in the paired bootstrap, you don't even need the assumption of the homoscedasticity. So this is an interesting thing. So here is the histogram of the paired bootstrap regression. The sampling, you can say this is the bootstrap sampling distribution. Bootstrap sampling distribution for alpha and beta. Okay, and we can see that 0 is somewhere here. So this is pretty much including the 0, the distribution, and we can see that 1 is somewhere here. So beta definitely including 1, whereas and alpha distribution concluding 0. So it is fairly priced, and the confidence interval for beta says that most likely it is as much risky as the overall market. Here is, we found the residual bootstrap regression also. What we found that residual bootstrap alpha is pretty much same. Even the confidence interval are also pretty much similar, and paired bootstrap, because one of the reason is both we found that the in CAPM, when we studied this, that homoscedasticity was okay assumption. So naturally residual bootstrap will be fine. So naturally paired bootstrap and residual bootstrap tend to agree on each other. Okay, so here is the residual bootstrap regression, the similar kind of distribution we are finding here. Here is another additional advantage of bootstrap regression technique. So in OLS method, if you just use OLS method with the normality assumption on the residual, the R square turns out to be 0.345. Okay, now because you have bootstrap samples, in each bootstrap sample you can calculate the R square, and so you can find a confidence interval for R square, which regular off the shelf regression analysis cannot produce. So off the shelf regression analysis cannot produce the regular R square, the confidence interval for regular R square, but bootstrap regression can give you a confidence interval for R square. Okay, so this is an advantage of bootstrap regression idea. So the idea of bootstrap statistics or resampling technique can be found in the idea of random forest, ensemble model, bagging. So in the machine learning technique, bootstrap statistics is almost everywhere. In many techniques are being kind of inspired by the bootstrap statistics. Random forest was, I think, around 2002 or 2003 was developed. Ensemble model was also in that time, bagging followed by bagging. So with that, I will stop here. Thank you very much. See you in the next video with hands-on. Thank you. Bye.